Hey everybody. So it's been a little while since we last did this, but this quarter we're going to move into chemistry. And specifically, I know this is biology class, but what we mean by that is we are studying something called biochemistry, which is oftentimes referred to as organic chemistry. So when you hear the word organic, it's not the same as what you would buy at the grocery store if something was organic that you were purchasing. When we talk about organic things in chemistry, it refers to carbon-based compounds, and carbon is one of the most important elements that we'll be looking at here in chapter 2 as we talk through biochemistry. So we're switching gears here from the big picture kind of ecology, ecosystem, food chain kind of idea. We're looking at large groups of populations interacting and so on. Now we're going back to kind of the simplest types of things that we can look at on a biological level. So the smallest things, the most microscopic things. And in this case, when we talk about the chemistry of living things, the biochemistry, as we'll call it, we're talking about things that are submicroscopic, so things that we cannot see. So you can see in this picture, we have double helical DNA. We have some test tubes with different things in them. But obviously, this would be an example of a molecule that we just can't see, looking at it, even with a microscope. You have to have something even more powerful than that. And sometimes that involves things like X-rays or other types of like electron guns and things like that. So definitely we're not going to be looking at anything here, but we are going to talk about kind of the chemistry and the makeup of our cells. And then as we go through the remainder of the quarter, we're going to look at cells, specifically organelles, cell division, protein production, what's the function of different cells in the body and how do they grow, that kind of thing. And then we're also going to look at photosynthesis and cellular respiration in a little bit more detail. I know that we briefly talked about them in our ecology unit, but we're going to look at specifically the processes, the organelles, and the chemical reactions involved in doing those processes, okay? So chapter 2 is going to be our lead in for really the remainder of the year. We're going to work our way back to a larger picture from this point on. So we're going to go again teeny tiny here. We're going to work our way back up to eventually look at populations again in something like evolution, and that'll be after spring break. Okay, so get the heading for me here. Chapter 2, the chemistry of life. I would normally say that this is something that is going to be reviewed for you, but it's very likely that this is something that you have forgotten. Even if you did it back in 7th grade or 6th grade, this is going to be pulling from information a while back. So used to be that in 8th grade y'all covered this, but it's my understanding that we don't do that anymore in 8th grade. So that being said, these first couple sections may be kind of tricky. So make sure you're paying extra attention, make sure you're writing down important information, and make sure you ask questions if you need help with any of these things, okay? So here's our section title, section 2.1, the nature of matter. So what we see on this image is a computer-generated picture of an atom, all right? And this is the centermost part of an atom, which hopefully you've heard of this before. It's called the nucleus, and the nucleus contains what we call subatomic particles, so things that are smaller than the size of the atom. So here are our learning objectives for this first section. The first one is the thing that we're going to cover first, the 3 subatomic particles that make up atoms, looking at isotopes, compounds, and then types of bonds. And in total in chapter 2, we're going to talk about 4 important types of bonds. We will only do 2 of those here in section 2.1. All right, so the remainder will come later on in this chapter. Okay, so atomic structure, go ahead and put the heading here. You can see I've got a vocab term there in atom, and I would go ahead and jot down the bullet below that also. All right, so atom is the smallest, most basic unit of matter. You may remember talking about living versus non-living things earlier in the year. And remember, we talked about the fact that a cell is the smallest and most basic unit of life. Now we're looking at things even smaller than that. So these are atoms, which combine and interact in certain ways to create structures that then make cells. Okay, but atoms do not define something as living. Atoms make up the computer screen that you're looking at. Atoms make up the paper that you're writing on. Atoms make up the pen or the pencil that you're writing with. Atoms make up my skin and my hair and really everything, right? Living and non-living. What we know about atoms is kind of complex. We're going to try and stick with the simplest information about atoms as far as what we need to know here to do well in chapter 2. So, of those things that you need to know, you definitely need to know the parts of an atom, and there are 3 parts that you should be familiar with. You can see them here on the screen. We have protons, we have neutrons, and we have electrons, and I believe, this is going to highlight those for you. So protons, if you can see in the image here, have a positive charge. And that means exactly what you would think it was, and that it also is attractive to negatively charged particles like electrons. Okay, so positive and negative still attract, just like you probably learned in the past. And those positive charges, those protons, hang out in that centermost part of an atom, which we call the nucleus. Okay. Within the nucleus, they're going to be interacting with neutrons, which I'll get to in a second. The next atom that's highlighted here is electrons, and those have negative charges. And notice they are not found in the nucleus. Electrons are found outside of the nucleus, and they kind of move around an atom in these things that we call shells or orbitals. When I was in school, we called them shells. Now we call them more of an electron cloud or orbitals in which these things will be moving. Okay, and we'll talk about them more in just a little bit when we look at how we diagram these. Neutrons, like I mentioned, are also found in the nucleus of an atom, and those neutrons do not have a charge. So they're uncharged, or they're what we call neutral. All right. So the only thing that they contribute to an atom is actually going to be mass. Right. They are worth some mass, and they do contribute to the weight of that atom, but they do not do anything in terms of an atom's charge. Okay. Now, how we distinguish between different types of atoms and elements is, I'm going to shift this guy over here, is is by looking at the numbers of these particles found in these different atoms. So that's actually what we're going to use to distinguish elements, and we'll look at that in a second. So again, here you have the same heading that we had before, so you don't need to rewrite that. And then the second item down there, subatomic particles that make up atoms are protons, neutrons, electrons. You should have also had that from the last slide. So that means the only things that you're going to write are going to be these, and I would definitely say you want to make sure you get all of these in your notes, because all of these are good informational pieces. And I know it's a lot on this slide. It's also going to be a lot for me to talk through. So if I can talk through it, if I can type all this up, you can certainly jot it down and pause if you need to. Okay, so protons, as I said, have a positive charge. I like to remember that by thinking, okay, P for proton and P for positive, and these two things go together. Okay, they're found in the nucleus along with neutrons, and there they contribute not only to the charge of an atom, but also to the mass of an atom. So they contribute to mass and also the charge. This is what we represent as something called the atomic number on the periodic table, and I'll show you what that is in just a few minutes. I've got that coming up here on another slide. Neutrons, on the other hand, are neutral in charge. They are uncharged. They are found in the nucleus, again, along with our protons. The only thing they contribute to, again, is, like protons, the mass of an atom. Okay, and I should probably add that these are also charge and mass. Okay, so we only get the mass of an atom here by contributing or by looking at protons plus neutrons. So when we look at the periodic table and we look at an element symbol, which I'll show you in a second, one of the things that we can't just kind of look at on the surface is a number of neutrons. It's not represented by anything as displayed on the periodic table. It's something that we have to actually calculate. So the way that we calculate how many neutrons are actually in a given atom of an element is by using this formula here. So we already know that the atomic number here is represented by the number of protons. The atomic mass is going to be something that we see on the periodic table also. All right, but the proton number is what we're looking at here with the atomic number. So as long as you can identify an element like the little square on the periodic table, which we'll see, and you know which one I'm asking for, you should be able to calculate protons and neutrons from that. The last item that we see when we talk about atomic structure are electrons. And electrons have a negative charge. If I kind of shorthand these, which I do often, like I don't write out the whole word electrons, I shorthand it and I write out this little e with a negative charge. So if you see that in my notes, that's what I'm referring to, where I'm talking about electrons specifically, and I put the little dash there to represent the fact that it's got a negative charge. These, unlike protons and neutrons, again, are found outside of the nucleus. We find them in places like the electron cloud or in what we call orbitals. All right, and each little orbital or level or shell surrounding the nucleus can hold a certain maximum number of electrons, and we'll look at what those are in just a second also. Okay, we know that for most atoms, if a question is asked about any atom of any element, we can assume that they're going to be neutral in charge unless you hear otherwise. And for atoms that are going to be neutral in charge, that means that they have to have equal numbers of protons and electrons, right? Our positives must be equal to our negatives, all right? So if we can calculate then the number of protons by looking at the atomic number, that then means we can also calculate my number of electrons, okay? So for an atom of an element like carbon, which is atomic number 6, we would know based on this, okay, my atomic number represents my number of protons. So that would mean I have 6 positive charges. And my number of positives must equal my number of negatives. My number of protons must equal my number of electrons. And if I have 6 protons, I must also have 6 electrons. Okay, and then I can also go in and calculate neutrons. So understanding how we get these numbers is going to be important, especially as we move into looking at how these things interact and form bonds to then create cell structures and important molecules there. Okay, so again, make sure you have this information jotted down. I'm going to go and skip actually this next slide. I want to draw some atomic structure pieces here with you, but I do want to show you the periodic table here first. Okay, so this is our periodic table, and this is one of many. Honestly, I went on to Google and I Google searched periodic table and I found an image that I kind of liked and I stuck it here for you. Okay, if you don't like the way that this one's organized or the colors or whatever, if it's too busy for you, you can certainly find any other representation of one, whatever works for you. So when we look at the periodic table, a couple of things that we want to kind of take note of, and I'm not going to ask you on a test specific information about the way that the periodic table is organized, but just so we're kind of understanding why it is set up this way. Over here on this side of my table are my metals. Now, hydrogen is kind of an exception. It's placed there because it has 1 proton and it sits on that side. But for everything else there, you can see highlighted in orange and yellow here are the alkali metals and the alkaline earth metals. So my metals sit on that side, and my metals tend to have positive charges. All right, they tend to have positive charges because of their numbers of electrons. And we'll talk about those a little bit when we get into bonds here in a few minutes. But those metals there tend to like to interact, at least in some forms, okay, some forms of bonds, with these guys over here, which are my non-metals. All right, and my non-metals here tend to either be neutral in charge, so meaning that they don't have a charge, so I'll do like a 0 with a line through it there, or they tend to be negatively charged, all right, because they like to actually pick up electrons. And again, that's going to be based on kind of their structure and how they want to interact and form bonds with one another. Okay, so metals and nonmetals like to interact in certain ways. Nonmetals like to interact in certain ways. But you can see the ones that we're going to focus on the most, at least for our purposes, are going to be towards the top of this periodic table. So if we highlight some of those, the ones I'm looking at, hydrogen, sodium, magnesium, lithium, potassium, calcium, carbon, boron, nitrogen, oxygen, obviously, chlorine, sulfur, phosphorus, silicon, aluminum. So most of the elements that we see in living things tend to be up towards the top of the periodic table. All right, and those are going to be the ones you hear me talk about. We are not worried at all about these guys down here because those are typically not elements that we see in living things. And if we do, they're present in very, very small amounts. Okay, so if we take a step back, all right, we're going to look at one specific type of element here for actually creating a little diagram. And let's start with maybe our most important element for this section, which is carbon. Now, if you can't quite see what's on there, and I'm trying to see it too, there are some important pieces of information we have to pull from this little square. So the 6 that you see up here at the top, this is what we use to represent our atomic number. All right, and you will want to jot this down. It may be helpful to actually just kind of draw out this square with the digits in it, with the numbers in it, and label those accordingly. Okay, so we've got the atomic number up there. That's a small number that's always at the top of one of these squares on any periodic table. And then we have a number with a decimal. All right, so that number with a decimal right here is 12.0107, and that represents our atomic mass. All right, now remember these two things mean different things for specific atoms of different elements. Also in that square, we have the element symbol, which is C for carbon, and the element name, which is just carbon, okay? So make sure you jot that down as an example. Let me scoop back here so we can actually draw some of these things out. So when we look at an atom of carbon, again, the information we need to pull from that is going to be based on those numbers that were given in the periodic table. All right, so if we're starting with, I have C, and I've got my element name, I have the number 6, and then I'm just going to simplify this and make this 12.01. So this is kind of my square from my periodic table. All right, so again, some of those items that we just talked about that we could actually label on this, we have our atomic number, and we have our atomic mass. And then also in there, again, we have our element symbol, and we have our element name. Sorry about my handwriting. It's tough to write on this. I'm writing with my finger and not with a stylus, so it makes it a little bit tricky. All right, so when we looked at the notes previously about protons, neutrons, and electrons, what we identified was that the atomic number represents the number of protons. Okay, so I know that if my atomic number here is 6, my number of protons is also going to be 6, okay, because these two here are equivalent. Now, number of protons, remember, is representing the number of positive charges. That's looking pretty ugly here. So let me try that again. The number of positive charges in this atom. Now, equivalent to that is going to be the numbers of negative charges, right? Because I said all atoms of any element, we can make the assumption are going to be also neutral, okay, unless we're told otherwise. So that means my atomic number is also equal to my number of electrons. And so my number of electrons then becomes 6. All right, my positives and my negatives are equal to each other, so I have a net neutral atom. Now, to figure out my number of neutrons, remember I have to do a little bit of math for this one, and it's not complicated math. What I do is I take my mass minus the atomic number. So I'm going to say 12.01 minus 6, because my atomic mass is 12.01, and my atomic number is 6. All right, and so that leaves me with a total number of neutrons of, again, 6. Now, obviously, it could be 6.01, but we truly don't leave the 0.01. We're going to say that on average, an atom of carbon has 6 neutrons. Now, the fact that there is a decimal there indicates to us that there are going to be examples of carbon atoms in the universe that have maybe 7 neutrons in the nucleus, okay? So that's why we see that decimal there. But for our purposes, we round it and we get the nearest whole number, okay? All right, so when we go to actually draw an atom of this, the first thing I always start with is going to be my nucleus. So I'm going to draw a circle here to represent my nucleus, and maybe yours is going to be better than mine. Inside the nucleus, remember, we have 6 protons, so 6p. That looks not so good. Oh, no. Let me put it all back. Maybe. There we go. Okay. So 6p, let me just erase that little p because that looks pretty bad. So we have 6 protons here in our nucleus. All right, now also in our nucleus, along with those 6 positive charges, is our 6 neutrons. So I'm going to also put 6 neutrons in there. All right, and then in addition to that, I'm going to have let me see if I can fix this 6 also. Let's try one more time. So 6 neutrons. All right. Now, in addition to what's in the nucleus, I know that I also have energy levels and what we call orbitals here, where my electrons are going to be kind of floating around. And so for those, because they're not like specifically solidified levels and areas, I generally draw these as levels with dashed lines to represent that they're kind of fluid. They don't just stay in one spot, and they're kind of always moving around. Okay, so if you do it with a dashed line, that kind of indicates that it's not just stagnant like the nucleus would be. So these are going to be my energy levels, and we'll label them in a second. But notice that I drew 2 of those. And the reason for that is going to be pretty important. How we place electrons in our atoms like this is going to play a big, big role in determining how these things bond and interact and form molecules and then form cells. So to understand how we place electrons in here, we have to follow a rule, and that rule is called the octet rule. Okay, and the octet rule kind of determines exactly how many electrons can go in these different energy levels. For any atom of any element, the first energy level can accommodate a maximum of 2 electrons. That's it. Okay, so for an atom of an element like hydrogen that only has 1 electron, we just stick 1 electron in the first energy level and we're done. But for atoms of elements beyond hydrogen and helium that have 3 and more electrons, that means we now have to branch out and start to use a second energy level. So my second energy level here, according to my octet rule, this is where we get the term octet, we can fit a maximum of 8 electrons. Okay, so that's where the octet piece is coming from. The third energy level, we can also fit 8 electrons. And honestly, for living things, we don't tend to get any bigger than that in terms of the atoms that make us up. But in case we were wondering, or in case we're ever presented with that situation, the 4th energy level can actually fit 18 electrons, which is kind of massive. So here we have 2 energy levels. We always fill them from the innermost or first to the outside, to the 4th or beyond. Okay, so we go kind of in this direction, and you have to fill them up before you move on. Okay, so for carbon, remember I have 6 electrons, and I need to place those in here. And so the way I'm going to do that is I'm just going to draw some dots here to represent my electrons here in this space. Okay, so I've got 2 there in the first, right? I've got 1, 2, 3, 4 here in the second. Now, notice how I kind of space those out, and the reason for that is just because we know that like charges tend to repel, and all electrons have a negative charge, so they don't tend to want to hang out together in this atomic structure. So I just spread them out. Okay, let's do another couple of labels here, and then we'll move on from this. So these are, again, my energy levels. Again, I have 2. Here is my nucleus. Okay, only one of those per atom, and that one is going to be pretty important to determining mass and also what type of element it is. And then I did leave off one other thing involving this. What you just drew here is called a Bohr diagram. B-O-H-R, diagram. The other thing I just want to point out is that there are other ways of representing atoms and their structures, specifically involving the outermost electrons. So the electrons that I drew on the very, very outside, the 4 that you see here, so this guy and this guy and this guy and this guy, are what we call valence electrons. So they are on the outside. And the valence electrons have everything to do with how atoms interact with each other to form bonds. The last type of thing that we can do with this when we're looking at diagramming atoms is actually to, I'm trying to get my eraser here, I'm going to erase part of this over here, is actually to represent exactly the number of just the outermost electrons. So in other words, if we're not interested in kind of diagramming the entire thing, but we do need to know how many electrons are present in terms of how it can interact with something else, the way that we do that is simply by looking at the number of valence electrons. This diagram is called a Lewis structure or a Lewis dot structure sometimes. And Lewis structures are super simple. They're as simple as this. So you write down the element symbol, which in our case, this is carbon, so it's C. I should probably do an arrow here. This is my Lewis structure. And like I said, we can count how many electrons we have on the outside, and we have 1, 2, 3, and 4. So what I do in my Lewis structure is I just take and I'm going to place 4 dots on the outside of this carbon symbol. That's it. Okay, so that's my Lewis structure for an atom of carbon. It just indicates how many electrons are present, and it shows me here, actually, in this case, that I have the ability to form 4 bonds using those 4 outermost electrons. Okay, so that is a Lewis structure. If you hear that, that's what it's coming from. It's simply representing, again, the number of valence electrons being represented in a diagram of that atom. All right, so make sure you have that jotted down. And so what we're looking at here is more specific information about elements, okay? So again, you've got vocab, make sure you jot down vocab. Again, like I said, one of the things that we know is going to remain constant for any element and any atom of any element in the periodic table is going to be those atomic numbers and atomic masses that you see in the periodic table. Elements, by definition, cannot be broken down by natural processes. That does not mean that humans can't do it, right? We've come up with other types of human-initiated and chemical processes where we can split atoms. But for the most part, naturally, just universally, these things just don't break down on their own. Atoms of different elements are defined by their numbers of protons. So that's why we use the atomic number to kind of organize our periodic table. Number of protons will always stay the same, but the number of neutrons and electrons can actually vary when we look at atoms of different elements. And that's what we're going to look at next. This is where we get terms like isotopes and ions. Okay. So of the elements that we're looking at, again, I mentioned this earlier, these are the ones that we're going to focus on the most, especially the ones that are in red there and then hydrogen up there on your left. I don't care that you know the actual percentage here. This number here is not, neither of these are really going to be helpful, I don't think, come test time, because I'm not going to ask you that specific question, but you will hear and see me talking an awful lot about these 4 elements and then these few that we see down here, because those are the ones that we focus on the most, because those are most impactful, especially in the human body and for other living things. Okay, so we are focused only on what we call biochemistry, right, and organic chemistry, dealing with carbon-based compounds and those things kind of at the top of this periodic table. Okay, so isotopes, this is where I was talking about we can have different numbers of other types of subatomic particles, not protons, but in this case, we're looking at different numbers of neutrons. So isotopes of one type of element, and here's vocab, so make sure you jot it down, have the same number of electrons, but they differ in their number of neutrons. So again, like I mentioned to you earlier, when we talk about neutrons, we're really looking at the mass of an atom, okay? Nothing more. Neutrons have nothing to do with charge, simply with the mass. So when we look at isotopes, their atomic masses are going to differ, but they have the same chemical properties, meaning their reactivity is going to be the same. So meaning who they interact with, other atoms, other elements, do they form bonds? Are they covalent? Are they ionic? Are they hydrogen? Those things that we're going to be getting to here in the remainder of this chapter have really nothing to do with the number of neutrons. Okay, it's the electrons and protons that matter for those. So when we look at isotopes of carbon, like I said, all carbon atoms, being that they are of the element carbon, have to have the same number of protons. They all have the same atomic number, which is, again, 6. Remember, this is what we diagrammed. Number of electrons for all of these also, because we're assuming that they're neutral, nothing here tells me that something has a charge. And as a result of that, those positives must equal those negatives, and we end up with 6s going all the way down here. Also, every one of those atoms and isotopes, as we're calling them here, are equal in terms of charges. They're all neutral, okay? Now, the number of neutrons is what makes each of these different. You can see over here on the left, I have some different numbers. I have carbon 12, carbon 13, and carbon 14. And where we're getting those numbers is really by adding these two here together. So I'm adding the 6 plus the 8 to get 14. I'm adding 6 plus 7 to get 13. I'm adding 6 plus 6 to get 12. So as we saw the atomic mass of carbon, the average there is about 12.01, which means that most of the isotopes of carbon that exist on the planet are in the form of carbon-12. When we look at carbon in living things, that tends to be what we see the most, but sometimes we can use something called carbon-14 for radioactive dating, which can tell us the age of things like fossils. So there are, limited finite quantities of other types of carbon in our universe and on our planet, and those can be helpful for doing things like that. But for the most part, we sit at carbon-12, okay? So those are isotopes. Again, they differ in mass, not in charge. Okay, so when we look at charges, which we'll be getting to here on the next slide, we're going to look at compounds. So compounds are how we interact, how atoms interact with one another. And these can be atoms of the same element or atoms of different elements. When we talk about compounds specifically, we want to look at different types of elements. So 2 or more elements that are interacting in definite proportions. So this could be something as simple as water. Okay, this could be something as simple as ammonium or ammonia, which we talked about with the nitrogen cycle. This could be something as simple as carbon dioxide or carbon monoxide or methane, CH4. Any of those are examples of compounds. Compounds and molecules can result when bonds form between atoms that are unstable on their own, and these bonds can be of a couple of different types. You can see down here I've got the word ionic and I have the word covalent. So ionic and covalent bonds are the two we talk about in this first section. We're going to come back and talk about 2 additional types of bonds in sections 2.2 and 2.3 a little bit later this week and next. Okay. So the physical and chemical properties of a compound can be very, very different from those of individual elements. And we see that especially in things like sodium chloride. All right, and looking at specifically how sodium is reactive when not placed in a compound like that. Okay, and I'll show you that here on our next slide. But on the bottom here, you can see lots of different types of what we call organic compounds. These are all carbon-based compounds. And just so we understand, all these little single lines that we see here, these 3 lines, or the single lines, or the double lines, these are all representing bonds. Okay, and the more lines we have, the stronger that bond is. So if we have 3 lines, we actually call this a triple bond because there are 3. If we have 2 lines, we call that a double bond, and a single bond is just the one single line. But they all represent kind of the same thing, which is how these atoms are actually interacting with each other. Okay, so make sure you've got this information on this slide. Again, we're going to define ionic and covalent here in just a second if you want to hold off on that last bullet. All right, so when we talk about different types of bonds, like I said, it's not the neutrons that matter when we form compounds because that only affects the mass. What matters is my balance of charges. And so when we look at atoms that have charges, what that means is we've got atoms that have either gained or lost electrons. So ions are the term that we use for any type of atom that has either gained or lost in electrons. Now, why an atom would do this may seem kind of like what's the purpose here, right? Well, we know that atoms are pretty unstable if they haven't met their octet rule. And what I mean by that is if we're looking at an atom of an element like sodium here on the screen. So this is sodium. Na is sodium. Okay, and if we're looking at a sodium atom, well, sodium on my periodic table sits way, way, way on the far left side. Okay, way down on the left side. And so, sorry, and not on the left, I mean on the right side. That was my mistake. I'm mixing up my right and my left here on the screen. So sodium tends to sit on the right side in the first column, kind of beneath hydrogen. Okay, and if you're not sure of what I mean by that, you're welcome to go flip back and look at a periodic table to kind of refer back to. But sodium sits under lithium and also under hydrogen in that very, very first column. And what that tells us is that that is a type of metal. And sodium being a metal, what we know about metals is that they like to give up electrons because they're not stable otherwise. They're not real comfortable in this type of situation here where they have this one random electron sitting outside in its third energy level. Remember, our octet rule tells us that we want to have 8 in that outermost energy level. And so when we look at sodium that's only got 1 out there by itself, well, sodium has a couple of options to make itself feel a little bit better, to make it feel more content. What it can either do is it can take this 1 electron and it can get rid of it and kind of kick it out and just be left with the 10 that remain, or it can try and bring in 7. All right, now what I always say when I talk about this in class is going to be, which one of those options sounds easier? Is it easier to try and pick up 7, or is it going to be easier to just kick off 1? And without a doubt, the answer is always get rid of 1, right? I mean, why would I try and keep 1 if I had to then grab 7 more? So that's definitely what sodium likes to do. It likes to get rid of that 1 extra, what we call valence electron, the 1 outermost electron. And when it gives it up, it becomes a little bit more stable. Now, the problem is it has to have somewhere to go. Electrons just can't float in space freely. So when we look at sodium, when it gives up electrons, we know that it's interacting with something as a result of that there has to be another atom around of another type of element that actually has wanted that 1 electron that gets lost and has picked it up. All right, and then that forms what we call an ionic bond, okay? But in any scenario, regardless of which type of atom, of which type of element I'm looking at, ions by definition are just something that has a charge, and they get these charges again by either gaining or losing electrons. All right, now one kind of extra piece to kind of point out here, which I've said a few times, but I haven't really clarified. Because electrons have a negative charge, when we lose an electron, we actually gain a positive charge on the atom. So sodium here has 10 electrons after it's lost the first one, but its atomic number is actually 11. So it's got 11 protons with positive charges. That means if I compare those two numbers, I end up with an ion that has a positive, a +1 charge overall. I've got 1 more proton, then I have negative electrons, and they no longer balance. So my positively charged sodium will be happy to interact with something that's negatively charged and that has maybe picked up an electron. So this would be something to jot down. If you lose an electron, let me rewrite that. Lose an electron, you gain a positive charge. And when you gain an electron, and these are going to be atoms that tend to sit at the other side of the periodic table, you actually gain a negative charge, right? You want to keep in mind if electrons are negatively charged and we gain an electron, that means we're bringing in a negative charge, right? And atoms can gain more electrons than just 1. They can lose more than just 1. But either way, depending upon which way we're going, that determines what the charge becomes. Okay, so I mentioned ionic bonds on the last slide, right, with sodium, and here we see sodium again. So ionic bonds, by definition, these are things that form when 2 or more ions attract one another, and then they remain close together. This is not a physical attachment. I mean, look at this. This is an ionic bond, right? But there's nothing here in the middle. There's nothing that's actually attaching them and holding them together. So because of this, ionic compounds are not very strong. These bonds are certainly not strong, and they dissolve in things like water. You think about how simple that must be, right? So you put sodium and chloride into water and it just falls apart. And we see that example in what we call salt. Sodium chloride, NaCl, is the same as what you find in salt that you put on your food. Okay, so sodium chloride is actually the fancy biochemical term, but salt is really what you call it when you go to the grocery store or when you're in culinary class and you're making something. So sodium chloride, will dissolve well in water. Sugar dissolves well in water. And it's not that sugar is ionic, but sugar is something that we call polar, and we'll come back to what that means in the next section. So what you're looking at here, if I can erase some of this for you, is kind of the before and the after here. So what I'm starting with here on the left, of the screen is my initial kind of setup for this. So this is what sodium and chloride look like before anything happens. So sodium, as I said, is atomic number 11. Chlorine is atomic number 17. That means that sodium has one valence electron on the outside. So one valence electron. And sodium, however, has 2 plus 8 plus 7 to get to 17 electrons. So it's got 7 valence electrons. And what that tells us is that neither of these two atoms by themselves satisfy this octet rule. Sodium by itself is super reactive because it hates having that outermost electron sitting there all by itself. Chlorine is equally maybe reactive and certainly deadly to humans if it's left in this state kind of by itself. It does not like to kind of lack that last electron in its outermost energy level. So what we know that these two like to do is that they love to interact with each other. What that means is that we start with two atoms that have no charges, right, but are highly reactive, that are going to transfer. We transfer this one valence electron from sodium over to chlorine, and this is the one right here that we just added. All right, that's the one that came here from my original place in sodium. And we add that here in chlorine, and what we end up with is now some different charges. So sodium, again, has a negative 10 charge, has 10 electrons, 10 negative charges. Let me move myself up here. Chlorine, on the other hand, if you count, has now an additional electron. So where it first had 17 and 7 valence, it's now got 18 or 8 valence electrons. And so what that gives me is a single negative charge on chlorine, a -1 charge. Sodium has that +1 charge, and these two, because they want to kind of become maybe neutral, they interact happily with each other because, again, opposite charges interact. Okay, so ionic bonds are formed between ions that have gained or lost electrons, that have opposite charges and that attract one another. These are not physical attachments, so this is not a strong bond, and this is why these things can dissolve in water. Okay. The last type of bond we have to look at is called a covalent bond, and that's this one right here. So notice this one looks a little bit different. Covalent bonds, unlike ionic bonds, have nothing to do with charges. These tend to form between atoms of elements that don't necessarily want to try and gain or lose electrons. They don't want to fully give them up, and they don't want to pick them up either because they're kind of in the middle. Okay, so what I mean by that is sodium, remember, has just 1 electron, and it actually needs 8. Chlorine has 7 and needs 8. So those are really kind of at the opposite sides of the spectrum here. It's easy for them to pick up 1 or to get rid of 1, right? But if we look at an atom like this, which is oxygen, oxygen is atomic number 8, which means we have 8 protons and we have 8 electrons. And if we look at what that means here for my diagram, for my Bohr diagram here, I have 1, 2 electrons on the first energy level, and then I have 1, 2, 3, 4, 5. Whoops. Let me get rid of a couple of those. Some of these are actually coming from hydrogen. So the ones that I'm counting for oxygen, and I'll explain this in a second, 3, 4, 5, and 6. So I actually only have 6 valence electrons in this. And for this one, oxygen can do some different things. Sometimes it can pick up 2, but for the most part, it's going to hold on to its 6, and it's going to do something a little bit different. It's actually going to try and share its electrons with someone else that's in need. So instead of giving and taking, like we see with ionic bonds, covalent bonds form by sharing, okay? So hydrogens are atomic number 1. They have 1 proton and they have 1 electron. And hydrogen, being so small, doesn't really have to meet the octet rule so much, but it needs 2 in its first energy level to satisfy that first kind of part. And so what we see here is that it only has 1, and to fill and meet the requirement of having 2, it can either give up or pick up, or it can share. And so hydrogen, in the form of something like this water molecule you're looking at, likes to share its electrons. When it shares its electrons, everybody basically becomes happy in that they all kind of meet the requirements for electrons. So again, electrons in oxygen are 8. Total electrons when they share with hydrogen becomes like they have 10, which means oxygen kind of in this outermost energy level here is going to have what it needs in order to kind of maintain some stability. And hydrogen's here and its energy level will act like it has 2, and it's also more stable. So when we share with covalent types of bonds, we actually end up forming these really strong bonds. So covalent bonds are super strong and very difficult to break. So on this slide, make sure you get the information here on the left. When we form covalent bonds between atoms of different elements or even atoms of the same elements, like hydrogen and oxygen here on the screen, you can see this is where we form what we call molecules. So compounds are a little bit different. They involve atoms of different elements interacting together. Molecules, on the other hand, can involve atoms of the same or different elements, but the key is they have to have covalent bonds to be considered a molecule. Okay, so covalent bonds are the key for this. Again, the way that we represent these, you could see I've got what look like Bohr diagrams over here, minus, I didn't include here the protons and neutrons in the nucleus, but you can see the electrons being represented in those diagrams. My structural formulas here, my single lines again represent electrons, and in this case, we're talking about the number of electrons that are actually shared. So in HH here, this, I actually have 2 electrons. What I mean by that is if you look over here at this Bohr diagram, I actually have 2 electrons total. So that single line doesn't just represent a single bond. When we say single bond, we're actually referring to 2 electrons that are being shared. If I look at oxygen, I have 2 pairs of electrons being shared. And if you have like 2 pairs of shoes, right? How many total shoes do you have? You have 4. So this double bond here represents the fact that I actually have 4 electrons in that space. Okay, water, kind of same idea. I have 2 electrons being shared here, and I have another 2 here, so I have 2 single bonds. And methane here, there's 2 between each hydrogen and the carbon in the center. All right. So when we look at molecules that are found in living things, the majority of the things that are going to be important for us are made up of covalent bonds. The reason why we know that is because we know that we can take a shower and we do not dissolve and flow down the drain, right? If we did, if we were like the Wicked Witch of the West in the Wizard of Oz, right? I mean, then we would certainly be ionic. But the fact that we don't just kind of dissolve and become nothing when we get our hands wet or take a shower or run through the sprinkler out in the yard or whatever is important in that we're made up of covalent bonds, right? It's an important representation of that. All right, now, finally, last slide. Last thing we got to talk about are something called van der Waals forces. These are not chemical bonds, okay? These are weaker attractions. These are between 2 different molecules, which is why we're using the term here intermolecular. That's between 2 different molecules. Remember, inter, differ. So these are between 2 different molecules. This is an attraction between oppositely charged regions of nearby molecules. So they are, again, not bonds. They're weaker than even an ionic bond. They certainly don't hold up in water, but they are important in some areas. And the picture you're seeing an example of here is the forces that occur within kind of the extremities of certain types of lizards that allows them to do things like walk on water, okay? Or climb up, kind of, it looks like it appears that they're defying gravity, right? Those van der Waals forces are formed between the structures in the pads of their feet and then the surface that they're climbing on, okay? I would not expect to see much on van der Waals forces on your tests or quizzes for this chapter. Just be aware that they are this. I would know the definition, but beyond that, you're not going to have to explain anything more about these, okay? All right, so that was very long. I would highly, highly recommend that you go back and rewatch before we get to quiz and test time, because this is, again, that basic biochemistry stuff. And if you don't understand this, you're not going to understand the rest of the chapter, okay? So let me know if you've got any questions. Make sure you do the assignment that goes along with this and watch the videos. I think I'm going to put up a couple videos that tie into some of the content here. So make sure that you also watch those and play the quizzes, okay? Otherwise, I will talk to y'all later. Bye, guys.